All right, this is Brooks. I'm going to show you the Q learning algorithm. Just run it just while it's in the background. So here you'll see the code for the Q learning algorithm, or the Q learning algorithm. First, we start by taking in the initial state that we're going to be starting at and a racetrack. That initial state is set to this last state method, and then I have an empty result. Then the first thing I do is I put the state through the simulator, or no, first I calculate the policy. And this is just using mathematics or using there's like one function, I forget the name of it, but it uses that function to determine what the best action would be to take with the current state action pair. But there is like a 5% chance that it'll choose a non-greedy, but most of the time it will be greedy and choose what the best, like the max Q value would be. But sometimes, for the sake of exploration, it will choose not to, and it'll actually choose the anywhere from the third to fourth best. I don't think it'll ever consider anything that'll immediately lead to its demise, so it tries to stay in the top four. So then that method will return an action of what I should take for my next step. Then I put the current state and the racetrack and the action into a simulator, and the simulator will then tell me what happens if I crash, if I make it past the finish line, or if I should continue, and also the new state of the race car. So it returns in this result. The reward calculates the reward based on the return. You can see here if it's a crash, it's -1. If I continue, it's -0.4, just because I want to get to the finish line as fast as possible. And also it's out of the book. And also the finish returns a 1 because I want a reward for beating the track. Then let's see here. Then I calculate the Q value. This is using the Boltzmann distribution, I think so. Oh no, that's something else. This uses the Q learning function to calculate it. First, I take the Q value that's originally there, then I multiply the learning rate by reward plus the discount rate plus max value for the state. So that takes the maximum value or the maximum Q value for any of the actions of the given state. So it makes an action state pair and then finds the biggest Q value there. And then I subtract by the current value in the Q table. That gives a new one. Then I set the current value in the Q table to that new value, and I set the last state as the new state that was given by the simulator. And I iterate that over a number of times. So let me stop this, and I can kind of go through here and show you the learning, because there's some values here. Let me find a good one. Should we do a crash or yeah, let's do this one right here. This one finished in a success, and it did it in 5 steps. So first it starts by not accelerating, and sometimes it'll do this just because no acceleration has like the same Q value. So sometimes it'll pick it, and right here what you can see is the probability that I'm going to pick, given the current state pair, what I'm going to pick. You can see that it is learning. It's saying right now the best action to take is to go west, west and north. And I'll show you the track we're doing this on right now. West and north is the best direction. So over time, yeah, I am converging with this algorithm, and you can see that it'll even correct. It'll start accelerating east as it goes toward the finish line because it got a good path. So there you go. That is our Q learning algorithm.
Hi, my name is Christoph Finley, and I'm going to be doing a quick overview of our value iteration. So to begin, I have a debug track, which is like this. It's a 7x7 track that I'm going to be running through the value iteration algorithm. Let's start it. I'm going to be stepping through it with the debugger as fast as possible. So, trying to understand it. So to begin, we have a ton of constants. At the top here, we have little r, gamma. We have the success and failure of the card to listen to us, do what we want. We have max error, and then we have max change. This is all taken from pseudocode from the book, excuse me. So when I run the program, essentially what I want to be doing is I want to create a utility function, and I'll just scroll down here. The first thing I do is I have this while condition, and I essentially make my old utility function equal to my new, and then what happens is I update my new, and then this whole process repeats as many times as I want or until it converges, right? So I basically iterate through every state, and then I look through every substate. What do I mean when I say substate? Well, let me add a little debugger here, and we can step through this. So I'll show you the board really quick because it's a good visualization. This is what the board looks like. Initialized, every wall gets a utility value of -1, whereas every finish line gets a utility value of 1, and every track and start gets a utility value of 0. That's initialized. And I wanted to show you the reason there's a substate. So the walls have a substate of 1 because they're never going to change. I never need to consider different states, but for every XY position on the board, I need to have all of the different velocity permutations. So that's why I have 121 substates for this position. So you'll notice that this is the position 1, 2. And then I'll go to the next one. This is still the position 1, 2, but the velocity changed. That's the basic gist of this. So I have to consider a ton of states, and I have a really big table, and that's basically what happens. Next thing I do is I go to calculate the Bellman equation, which gives me basically a new utility, and I do that by doing the Q value. I'll just step through that so you can see what that looks like. Oh, whoops. I did this wrong. Awesome. Here. Q value. Perfect. So here's what the Q value calculation looks like, and then essentially what happens is it picks a utility value, which I use to update the board. And basically what this ends up doing is it creates it's going to run a bunch of times here, and it goes as many iterations as I want. It wasn't converging to me, so I just set a hard cap iteration, and basically what happens is I now have a utility function, and I'll just scroll up, and this is what it looks like. It's updated, so we'll look at one of the boards we were looking at before. Notice how these values will not be equal to 1 anymore. They will be equal to a bunch of random decimals, or doubles, and they're not the same. They're all different, right, for each state. So cool. That's basically showing the algorithm working. Next is I have this policy with the racetrack, and what happens is when I run this, let's make sure the debugger's good. I'm going to press go. It starts and it tries to drive somewhere, considers it, bam, and it gets there. So that's the algorithm